Okay, inverse relations and functions. And, you know, we will make a little bit of a distinction. Most of the time, we don't talk much about relations. So we really did. In chapter 2, when we started talking about domain and range and things like that, I mean, there was the thing of the most general term is a relation. And then if it meets certain criteria, we consider it a function. No repeated x values, passes vertical line test, things like that. So the most general term is to say something is a relation. It's a relationship between x's and y's. So that'll come up. But these are the SOL related objectives here. So consider this, right? Okay. Consider a function which would be your paycheck, how much you get paid as a function of the number of hours that you worked. Okay. And let's just say that you make $8 an hour. Okay. Then this would be the equation that describes that relationship. Right? Y equals 8 times x. Get off of that. Okay. If I worked 10 hours, I'm pulling 10 out of the domain of this function, how much money would I have made? $80, right? So 10 maps to 80. Okay, what if I work 20 hours? 20 times 8, 160. Okay. What if I work 30 hours? 20 or 30 times 8, 240. Okay, so that's a function. You tell me how many hours you work, I'll tell you how much your paycheck was. Good. Taylor. Okay. Right. The inverse of that would be, you tell me how much your paycheck was, I'll tell you how many hours you worked. That's what an inverse function does. It does exactly the opposite of what the function did. So for example, if you made, well, the equation for that would be now y equals 1/8 of x. Right? Now those numbers that we just generated, 80, 160, 240, now they're in the domain of the inverse function. Okay, so how many hours would you have worked if you made $80? 10. Right? If you worked 160, you would have worked 20. Right? If you made 240, you must have worked 30 hours. Right? So that's what we mean by inverse function. It's a function that does exactly the opposite of what the function did. Good. Okay. Right, if I put that together, right, here's the mapping diagram we made for the function, and here's the mapping diagram we just made for the inverse. So notice a couple things here, right? When we refer to the inverse, the notation is f to the minus 1. Like it's like an exponent in between the f and the parentheses x, right? So f to the minus 1 is inverse. Right. The other thing to notice is that the domain of the function is now the range of the inverse. The range of the function is the domain of the inverse. Right? When you go from a function to its inverse, you switch all the x's and the y's, which means you switch the domain and the range. And that becomes important by the end of this. It's like the last critical step in understanding this topic. Domains and ranges switch between a function and its inverse. Breathe. Okay. So functions and their inverses undo each other, right? Just like, and we already did this in this chapter, which is part of the reason why this is at the end of the chapter about radicals, right? A square and a square root, they undo each other. So they're inverses, right? The cube and a cubed root undo each other, right? That's how we solve the equations, right? We isolated and then we undid. Coming in. It's open. All righty. Okay. Functions and inverses, they undo each other. Okay. Let's go. Okay, so back to the fun and games. All right, so again, they're being careful at this first part to call these relations, not functions. So it might be a function, but they're just using a more general term. Okay. So here's the relation S and a table of values for it, right? In order to get the inverse of it, you switch the X's and the Y's. So now all the X's show up in the Y column, all the Y's show up in the X column. Sam. You good? Sorry. Okay, if you graph the points, right, you wanted to graph the inverse. Well, here's the set of points that were the inverse. And there they are, right? 0, -1, 2, 0, 3, 2, 4, 3. If all you're going to do is switch the X and the Y coordinates, then, right, 0, -1 becomes -1, 0. Right? 2, 0 becomes 0, 2. 3, 2 becomes 2, 3. And the last one, 4, 3 becomes 3, 4. Right? If you look at all those points together, I mean, we just took these 4 points, right? And they all got pushed up that way. Actually, they're now exactly the same distance across this line, which is the line y equals x, that they were on this side. Now they're on the other side. This line right here, y equals x, is a line of symmetry for the function and its inverse, right? That's one of the SOL essential learnings, right? A function and its inverse, their graphs are symmetric with respect to the line, y equals x. And that's what happens if you just switch the x's and the y's. What would happen to a point, which we don't have on here, but what if I had another point on here, which was -2, -2, right? And that would be right there. What would happen when I switch the x's and the y's? It's the same place, right? So, that's why this line right there is any point that's on it has to stay the same. And the points are on either side, it just flips them across the line to switch the x's and the y's. So try to make your table of values, which is the inverse of this relation. Again, put this on a separate piece of paper. You're going to hand it in at the end of class. All of the things that I say are you tries get handed in, and we'll get like a homework credit. Won't give it too much time because I know that's not going to take much time. The inverse x, y. 1, 2, 3, 4. Right, so before we had x is 0, 1, 2, 3. Now it's y equals 0, 1, 2, 3. Before we had y equals -5, -4, -3, -3. Now it's the x's. So what did that do to the domains and ranges? They just switched them. Okay. Now, looking at a table of values, how is it that you determine whether it's a function? If the x's repeat. So in this one here, would you say that it's a function? Yeah, this one is a function because there's no repeated x, right? Function. But what about the inverse? Here, you've got repeated x values now, so that is not a function. Good? Richard? Okay, now sketch their graphs. Graph the points and the inverse. Let's try red and make it a bigger dot. So 0, -5. 1, -4. 2, -3. 3, -3. Purple. That's still there. Now we've got -5, 0. -4, 1. -3, 2. -3, 3. So it looks something like that. And does it look like those points are symmetric with this line? Kind of a mirror image on each side? I mean, for a hand-drawn graph, yeah, pretty close. Again, that is the line, y equals x, which is the identity function because all the x's are equal to all the y's. That's why it goes through 0, 0. So let's get back to that, and that, and that. Okay. Now, if you have a graph, not just a table of values, if you have a graph, I mean, you can do the same kind of thing. Just grab a few points so you can see their coordinates and then switch the x's and the y's. So let's say for this y equals x squared plus 1, I can see a few points. It's a parabola, so I only need to have maybe like 3 points to tell where the parabola is going. How about if I pick this point? Oops, I want to be in blue. This point, and this point. Okay, that would have been negative 1, 2, 0, 1, and 1, 2. So what will be the table of values for the inverse? Just flip the x's and the y's. Okay, now if I plot those, right, I get 2, negative 1, 1, 0, and 2, 1. And can we see the shape of the graph by doing that? Looks like it's going like this. Something like that. And okay, it should look like that is, if I drew the line y equals x right through the middle, that 1 is just a flip across that line. Let's talk domain for a second, right? The domain of this function, just looking at the function, and you can look at the graph, but sometimes you can be deceived by the graph. Remember, by domain we mean, what are the x values you can plug in? Well, what are the x values you can't plug in? I mean, you can't plug in any x values that would lead to a divide by 0. And there's no dividing going on, so no problem. There's no square roots going on. So the domain of this thing is all real numbers. Right? That's going infinitely up and to the left, infinitely up and to the right. Domain. Why is that not clicking? Domain. All reals. The range, I mean, looking at the graph, are the y values all real numbers? Do they go infinitely down and infinitely up? Or do they stop at a certain point? They get down as low as 1, and then they'll go up again. So you would say that the range is y is greater than or equal to 1. Right, now look at the inverse. We would expect for the inverse that the domain and range have flipped. So the domain of this thing should be, for this one right here, should be domain x is greater than or equal to 1. And what should the range be? It should be the same as the domain of the function. So if that was all reals, then this is all reals. Okay, does that look right? Does it look like the domain is x greater than or equal to 1? Yeah, and I mean, these things, again, it's kind of hand-drawn, but is intended to be going up and to the right, down and to the right. Goes on forever. So it is going infinitely up and down. And if you're not sure about it, you just take for granted that, you know, whatever was the range, or sorry, whatever was the domain of the original, that is the range of this. Always. Okay, so try to do the same thing for this straight line, right? Y equals 3x plus 2. Right? You can make yourself a table of values, and because it's a straight line, how many points do I need in the table of values? You just need 2, right? You just need 2. So take 2 where it's pretty clear where it's crossing the intersection of the grid lines. Does anybody see some points in there? How about right there? Right? And how about right there? So what are those 2 points? It's just this one is -1, -1. Another point is 0, 2. Right? So flip those, plot them, sketch a line. Flipped them. What did you get when you flipped the -1, -1? Same thing, right? And then you got to put in the 2, 0, and now it's here. And I'll do it like this. What's my straight line? Solid and blue. Go, go, go. So do those look like they are mirror images across this line right there? One is just a flip across the line, and they do. That's what you expect. Back to that, back to that, back to that. Again, this is the line y. Why does it do that? Y equals x. Okay, we need inverse functions. I mean, the reason we study them is because we need them to solve equations that we can't solve algebraically, meaning you can isolate a variable by just doing the same thing to both sides, or even still factoring so that you could place each factor equal to, right? Even quadratic formula, all that's considered algebraic. There are some functions that can't be solved by doing things to both sides, doing the same things to both sides. And in fact, you've done them before. You have used them before. I don't know if anybody can remember when you used them, but you used them. Okay. All right, this is where you used this before. Maybe it'll ring a bell. In geometry, when you were solving right triangles, and you don't have to do this. You don't even have to write it down. I mean, I'm just trying to make you think of a time when you actually did use an inverse function. In this kind of a scenario, when you were trying to find an angle and you knew two sides. If you remember, you had to remember opposite, adjacent, hypotenuse. Okay, with respect to that angle, this is opposite and adjacent. So the function is tangent. So you would set up an equation. Tangent of x equals 23 over 34. Now, you can't solve for the x by dividing by tan, right? It doesn't work. That's actually a function notation, and the x is inside the function, right? So that's what we mean by a function that can't be solved by just dividing what's with the x to get rid of it. It's actually got a name. It's called a transcendental function. And what you did, what you may not even have realized it, is we use the inverse tangent function. If you do the tan inverse of the tan on both sides, or tan inverse of both sides, on this side, the tan inverse of the tan, that's the composition that we did in the last class. That is a composition of functions right there, okay? And what happened is the whole thing simplifies. When you do the tan inverse of the tan, they cancel each other out, and all you get is the x. So the way to peel back the tangent to get at the variable which is inside is you do an inverse function. But you still had to do the inverse function of the right. So on your calculator, right, if you look right above the tangent, you see tan inverse. And if you did this in geometry, you were using an inverse function then. Whether you realized it or not, you just used an inverse. I mean, it might be a little bit, confuse the issue a little bit. The first example that I gave, your pay and the number of hours you worked, right? One of them was y equals 8x, and the other one is y equals 1/8x. And 8 and 1/8, those are what you call multiplicative inverses, definitely. But we're not really talking about that, right? This is an inverse function. You know, this x to the minus 1 over here, that's doing the multiplicative inverse. It's flipping something upside down as a fraction, or, you know, reversing a fraction like that. These are inverse functions. So it's kind of a different thing, although, as we saw, it could actually be the inverse, to do 1 over something. It could be. But in general, it's not. Okay, so inverse functions. Now, this kind of thing, where you take the tan inverse of the tan and they cancel each other out, it doesn't always work, right? It doesn't. Let's see if it goes. This tan inverse of tan, again, I could write it with that composition notation, tan inverse, little open circle, tan. That means composition. It's the same thing. That's like saying f minus 1, the f inverse of f of x. And under certain circumstances, it is true that they cancel each other out, and you just get the x, which is inside, which helps us to solve equations like all the trig functions, logarithms, exponentials, lots of functions that can't be solved algebraically. We have to do this kind of a thing. And the condition for which this is true is that both the f and the f minus 1, they have to be functions. And since it's a graph, basically you're going to look at, they have to pass the vertical line test, or else you can't do this thing right here. Right, so f, and it doesn't matter the order, right? If I can do the f minus 1 of the f, or I can do the f of the f minus 1. It doesn't matter. In either case, they'll cancel each other out as long as both f and f minus 1 are functions. And you might look at it and say, well, we're using that little lowercase letter f. Doesn't that mean they're functions? And no, they're using that kind of in a more general sense. It could be a relation. I mean, go back to the two that we already did with a graph, right? The 3x plus 2, that was the u-try that you did. Here's the function, and here's the inverse. Do they both pass the vertical line test? Yeah, they would both pass a vertical line test. So both of these are functions, so that property would hold, right? This is linear, and the truth is that it always holds for linear. I mean, it's not like you're going to have to look at many graphs to determine whether the linear is going to hold. Right? This is linear, and I'll just say that it almost always both are functions. And the reason I'm going to say almost, because what is the one straight line that would fail a vertical line test? A vertical line, right? So that would be an exception to the rule. And for that same reason, a horizontal line would pass a vertical line test. But if you flipped it, it would be a vertical line, and that would fail a vertical line test. But unless you have a straight vertical or horizontal line, all the linear functions, they meet that criteria. So you can assume that f of f minus 1 cancel each other out. Okay, what about the parabola? The parabola was a function, right? We've already studied parabolas as functions. Was the inverse a function? Does it pass a vertical line test? No. So you can't use that same property with a quadratic because the inverse would not be a function. Again, well, you know, if I said what is f of 1 is 2, but I said what is f minus 1 of 2, I would either get 1 or I go negative 1. I wouldn't get a clear answer. A function only gives you one answer back. So this one is the inverse, not a function. Okay, so now we're going to learn, okay, so let's say we're given the equation of a function, and we want to find the inverse. Then we have some very finite steps here. One or two of which are almost, sometimes not necessary. Um, I mean, we know that sometimes you say f of x equals, and sometimes you say y equals. If you're given the function as f of x equals, then you want to replace the f of x with a y. A lot of times, in fact, in the homework, most of them, they don't have f of x. They just start with y equals. So you don't have to take that first step. It's already done. So once you've got it as y equals some expression of x, you switch the x and the y. Switch the domain and the range. And now by doing that, you just put y in the middle of the right-hand side. It's no longer solved for y. So you have to solve for y. And then you could replace the y with the f minus 1. That will be the inverse. Let's see if I got this here. Not that, not that. Maybe they don't have it. Okay. So we'll do a few of those. Right. Find the inverse. Y equals 3x plus 1. Okay, so the first step says replace f of x with y. It's already replaced. What should I do next? Switch the x and the y. X equals 3y plus 1. Then what? Solve for y, okay? Isolate the y. Okay, now this is algebraic. So what do I do to isolate the y? Subtract 1. X minus 1 equals 3y. One more thing. Divide by 3. Right, so we'll get y equals x minus 1 over 3. F to the minus 1 of x equals x minus 1 over 3. Right. There's no real issues with domain and range here. The domain and range of a linear, unless it's horizontal or vertical, which we've just said is not usually what we're going to be dealing with here. Unless it's horizontal or vertical, the domain and range is all real numbers. You can plug in anything, you can get anything. So no real domain issues. Okay. So I think it's one for you to try. Try to do the same thing with that. Write it on that same piece of paper I'm going to pick up. Who's got an answer? Sam. X minus 4 over negative 3. Anybody else get that? Okay. So you, again, this is the f of x, but since it wasn't written with an f of x, kind of like already had the first step done, we switch the x and the y, which again is switching domains and ranges. And then you solve for y. Subtract 4. Divide by negative 3. So this is y equals x minus 4 over negative 3. What if you wanted to get rid of that negative 3? You don't like the negative in the denominator, what could you do? Remember if you switch the order of subtraction, what does that do to the sum? 3 minus 1 is 2. 1 minus 3 is negative 2. So by switching the order of this, make it that 4 minus x, that would make that the opposite sign, and then you could just have 3. Same thing. You could multiply top and bottom by negative 1. You could say. Okay, and then you could replace it with a f minus 1 of x equals, I'll write it like you guys did, x minus 4 over negative 3. Right? It's not that hard of a process. At least those steps. And at least for this kind of function, you just got to remember the few steps that there are. Okay, graph a relation and its inverse. Okay, I put this in here just to show you. You're going to get a homework problem that's kind of like that. So you could graph it by graph it as a straight line because you know how to graph a straight line, or you could plot the points and then switch the x's and the y's and graph that too. How about if we do this? I'm going to find the inverse. That'll be x equals negative y plus 2. X minus 2 equals negative y. Multiply both sides by negative 1. Y equals negative x plus 2. So this is the f of x. Right, this is the f minus 1 of x. Plus 2 minus 2. Like I said, when you get this kind of problem in the homework, I kind of think that in their progression of where this laid in the lesson, that they might expect you're just going to plot some points, make a table of values, put in there 2 points, flip the x's and the y's, do that too. But we know this is a straight line, has a y-intercept of 2, right? Has a slope of negative 1, and that goes down 1, over 1. That's going to make it like this. Right, that's the f. And then for the inverse, actually the inverse is the same thing, isn't it? Which looks right? It's still plus 2, slope is negative 1. Does that look like, if you flip it across that line, it's still the same thing? Sure. I don't like that as an example, but. Okay, so then I think the most difficult problems you're going to get are going to be problems like this. And these are the directions that are exactly from that section. And it's because this gets back to the domain and the range issue. So when it says find the domain and range of the f of x, I'm going to do this here. I'm going to say, right, here's my f of x. Here's my f minus 1 of x. This is domain, and this is range. Okay, remember for functions, we're looking at the domain is all real numbers except for two situations, right? I can't divide by 0. No problem here because we're not dividing by anything. And I can't take the square root of a negative number. Okay, well here we are taking a square root. So I've got to find the domain which would make sure I don't take the square root of a negative number. And the way you do that is you take what's inside the square root and set it greater than or equal to 0. Just make it greater than or equal to 0. Right? Take this thing right here, right, x plus 7, and set it greater than or equal to 0. And then solve for x. X is greater than or equal to negative 7. So as long as I use x values that are at least negative 7, what's inside the square root will be a real number. It'll be positive, and then the square root will be a real number. What if I put in negative 8? Negative 8 plus 1 is negative 1. Now I've got an imaginary number, not in the domain. So the domain up here is x greater than or equal to negative 7. Okay, now we look at the range. Okay, well, what kind of function is it? Or it's a square root. What do we assume to be the values of square roots? Positive, right? It could be 0, or it could be positive, but it can't be less than 0. So we got to say that the range is y greater than 0. Actually, y greater than or equal to 0. Okay, so what do we know about the domain and range of the inverse? They flip, right? So if this had a domain of x greater than or equal to negative 7, this has a range of y greater than or equal to negative 7. If this had a range of y greater than or equal to 0, this has got a domain of x greater than or equal to 0. Right? I don't need to look at the inverse to know that. I know it, right? Because that's how it works with functions and their inverses. So now let's find the inverse here. Substitute f of x equals y. Switch the x and the y. Solve for y. Okay, how am I going to solve for y when it's inside a square root? Square it, right? I mean, now you can look at it like in the previous section of solving radical equations, right? You isolate the radical, which is already isolated, and then you undo the radical, square it. So when I do that, I'm going to get x squared equals y plus 7. So I'm almost done. Subtract 7. Y equals x squared minus 7. Okay, so this will be f minus 1 of x equals x squared minus 7. Let me see if I could do that on this slide right here. Right, if I looked at the graph of that, I mean, this is definitely a quadratic, right? It's a parabola. The y-intercept is this negative 7. So it's a parabola that's been moved down 7. I mean, that's a vertical shift down 7. So if I look at that, 1, 2, 3, 4, 5, 6, 7. It looks something like this, and this is just kind of sketched like that. But then you got to apply the domain, right? The domain says it's x greater than or equal to 0. Well, x greater than or equal to 0 is only the right side of that parabola, right? You would not include both sides because the domain says only include the x greater than or equal to 0 side. So you would have to go back and say take out this part right here. Now, this is the square root function. Okay, we don't know the square root function. That actually comes up in the next lesson. But we know that it's going to be a flip across the line y equals x of this. So that means that if this thing had a point on it which was 0, negative 7, this has got a point on it which is negative 7, 0. Right? If this thing went up like that, this thing is going to go up like that. There's y equals x going right through the middle of it. So here's the original function. Is it a function? Does this pass a vertical line test? Yeah. How about this piece? Does that pass a vertical line test? The right side of the parabola does. If we had, yeah, it does. Both of them do. So they're both functions. So when you're dealing with square root functions, then they'll both be functions, because you're only using, like, what we see now is that the square root function is 1/2 of a parabola that's been turned on its side. Same shape exactly. And right now I'm going to do the same thing with a quadratic. Right now this is a quadratic that has been moved up 2, and it's been stretched a little bit because of that factor of 2. If I looked at the graph, it would look something like this. Right, it's moved up 2, and it's a basic shape of a parabola. What would you say is the domain of that? Come on, don't do that. Okay, so you'd say the domain of this is all real numbers. No dividing, no square roots, all reals. Does it look like the range is all real numbers? Do the y values go infinitely up and down? How could you describe the y values? What's the least y value? 2. So how would you say that? Y greater than or equal to 2. Okay, so now what will be the domain of the inverse? X greater than or equal to 2. And what will be the range of the inverse? All real numbers. Okay, so now let's find the inverse. Y equals 2x squared plus 2. X equals 2y squared plus 2. X minus 2 equals 2y squared. Okay, divide by 2. X minus 2, y squared equals x minus 2 divided by 2. All right, now I'm still not done solving for y. How do I turn a y squared into a y? Take the square root of both sides, right? When I take the square root, remember now I'm taking the square root. I wasn't given a square root, which I assumed to be positive. I'm taking a square root. So I have to say y equals plus or minus the square root of x minus 2 over 2. F to the minus 1 of x equals plus or minus the square root of x minus 2 over 2. Okay, we know what this graph is going to look like, right? It should look like that parabola that I already started with. It just now it's been flipped across the line, y equals x. So if this is a parabola that opens up, then the inverse is going to look like a parabola which is opening to the right. Right? The plus and the minus half of this, the plus is the top half. The minus is the bottom half. Is the inverse a function? No, it fails the vertical line test, right? Except for 1 point, 2, 0. For every value you put in of x, you get 2 values of y. You get the plus and you get the minus, right? That's repeated x values if you had a table of values. Okay, last thing. If we have a function that it's a function and its inverse is also a function, then we know that this property, f of f minus 1, they cancel each other out. So when you see a problem like this, f of f minus 1 of 1, you have to look at the kind of function that you got. What do we say about linear? Linear is always a function and its inverse is always a function. So does the property hold? Yes. So what would be f of f minus 1 of 1? 1. It's just whatever's inside the parentheses. The f of f minus 1 cancel each other out because the linear is a function and its inverse is a function. What if I switch the order of the f of f minus 1 so it's f minus 1 of f? Doesn't matter. They still cancel each other out. What if we're doing some crazy value like pi? It doesn't matter. And a lot of times on these problems, they make that point by using kind of crazy numbers, like, huge numbers or square roots and all kinds of things that you don't really want to evaluate anything for. But it doesn't matter, right? As long as that's linear, then f of f minus 1 of anything is the same thing. Now, if that was like a quadratic, you wouldn't be able to do the same thing. But I've never seen the question asked that way. I've never seen them like do a trick on you. Then you really would have to find the inverse and then actually really take the composition of the function. But I've never seen it asked that way. It's always a linear function. So you can just like grab those. It should go like that. How about this one here? You don't even know at this point what I mean by E. But you do know what about f of f minus 1 of f. So what is the answer here? This is your last you tried. This is the last slide. What is the answer? E. That's it. Okay? Because, again, you don't just automatically say that. It's just because this is linear. Since that's to the first power, you know that it's going to be true. Okay, so that is a long, but you see, find the inverse of a function. Graph the inverse of a function as a reflection across the line y equals x. Okay, like I said, that's kind of an important thing. Okay. So that's homework. And you get handed